Now, if errors are normally distributed, if errors are normally distributed, then this would imply that beta hats are also distributed normally. Okay, so in order to know the distribution of estimators, you have to know the distribution of errors. So in case if you want to know how beta hats are distributed, you have to understand how UIs are distributed. Okay, so in case if you say that UI are normally distributed, this is one of your assumption that normality of errors, they are distributed with zero mean and sigma square variance. Okay, this means they are normally distributed. Okay, this means that they are normally distributed. They have zero mean, and here they have same variance. Okay, they have same variance. They are independently and identically distributed. They are independent of each other, and they have almost same variance. They are identically distributed. So what you do is that you form a test statistic. Okay, so well, why do you take up a t-test statistic? We'll let you know later on, but just for now, your t-test statistic is estimated minus hypothesized value upon standard deviation of estimated. Okay, so if you wanted to test that this beta 2 hat here, this beta 2 hat is equal to 0 or not, so what you do is you have an estimated value of beta 2 as beta 2 hat from your regression analysis. You have hypothesized this value of that the beta 2 should be equal to 0 under your null, so you'll put 0 upon standard deviation of beta 2 hat. Okay, this is the thing which you will be getting. Okay, now this is some of the very good statistical properties. Okay, so if estimated value, this value is actually big enough, then you can reject the hypothesis. But the question is that what exactly is big enough? So that is taken care of by the standard deviation. So if the estimated value, it lies outside almost say 2 standard deviation, then it is big enough to reject. Okay, this t statistic, it measures the number of standard deviation you are away from 0. Fine. Well, in case if you look at the standardized normal variate, standardized normal variate Z, that is nothing but x minus mu upon standard deviation. That is a standardized normal variate. Is almost like this. Okay, so what you do is that your estimated minus hypothesized upon standard deviation of estimated. Fine. So it is also measuring that how far this particular measure is how many standard deviations it is away from 0. 0 is actually the mean of the standard normal variate and all that. So well, so the question is that, is this enough standard deviation away from 0 to reject? Say for example, if n is equal to 25, fine. So let me just put it here. In case if n is equal to 25 in this case, okay, and well, for a two-tailed test, okay, at 5% level of significance, for a two-tailed test, this value will come out to be, yes, 2.08 here and 2.08 here. Fine. From t tables. Fine. In case if you have in case if you have 4 parameters to be estimated, beta 1, beta 2, beta 3, beta 4, supposedly if you have that kind of model. So in that case, this is what is actually the value? 0.05. This is the critical value, and this is say 2.08. If the calculated TC is greater than this critical value, then you reject the null hypothesis. You say this, that the hypothesis which you have maintained that beta 2 is equal to 0, that is wrong, and beta 2 is actually not equal to 0. So this is the meaning of beta 2 equal to, of null hypothesis equal to 0, or rejecting the null hypothesis.